Look at this graph of the standard cosine function. It oscillates smoothly and plots infinitely in both directions. But this endless repetition creates a mathematical paradox if you ever try to run it in reverse. Because the wave repeats every 2 pi, many input values produce the exact same output. Cosine of 0 is 1. Cosine of 2 pi is 1. Cosine of 4 pi is 1. This creates an immediate dilemma with inverse notation. Asking for the inverse cosine of 1 yields conflicting answers. You cannot have a single function that returns 0, 2 pi, and 4 pi simultaneously. In algebra, an inverse operation is only valid if the original function is strictly 1-to-1. One unique input must map to one unique output, and vice versa. Because natural trigonometric functions are inherently many-to-one, true inverse functions do not naturally exist for them. We have to artificially engineer the conditions for an inverse cosine to survive. To manufacture a 1-to-1 environment, we must ruthlessly slice the infinite wave into finite, non-repeating segments. Isolated in a vacuum, any of these individual slices represents a valid 1-to-1 curve. But mathematicians need a reliable, universal standard. By convention, we select the interval from 0 to pi. We label this specific standardized constraint the principal value branch. We can now define the strict parameters of our restricted cosine wave. The outputs, the geometric ratios, are tightly bounded between -1 and 1. The allowable inputs are also strictly confined. Our angle values can only exist between 0 and pi. This graph illustrates exactly how these bounds manifest geometrically. The ratios scan from 1 to -1 on the horizontal axes, constraining our valid angles to the top half of the unit circle. By actively discarding infinite amounts of valid data from the original wave, we have successfully forced a 1-to-1 environment. Inverse cosine now has the structural integrity it needs to function. With the boundary set, we can mechanically construct the inverse graph itself. The generation of an inverse function follows a rigid geometric law. The new graph is always a mirrored reflection of the parent graph across a diagonal axis where y equals x. This reflection happens because of a simple algebraic coordinate swap. Every data point, AB, on the parent curve trades places to become BA. As the restricted cosine curve folds across that dotted line, the definitive inverse cosine graph emerges in its place. We can verify this mechanical transformation point by point. The parent curve starts at the coordinate 0, 1. That exact point traverses the reflection threshold and locks into position at 1, 0. Notice the final result of this coordinate swap. The domain and range of the original restricted function have completely traded places on the x and y axes. This precise geometric reflection depends entirely on the existence of a rigorously constrained space. Now, we test these rules against a more volatile trigonometric function, the cosecant. Cosecant is defined by a foundational mathematical identity. It is the direct reciprocal of the sine wave, 1 divided by sine of x. This diagram shows the inherent vulnerability in that reciprocal relationship. Wherever sine equals 0, the cosecant attempts to divide by 0. These division by 0 errors create vertical asymptotes, violently fracturing the cosecant into disconnected upward and downward curving branches. The outputs of these fractured curves are extreme. The range only exists at absolute values greater than or equal to 1. This leaves a massive mathematical void in the center of the graph. The parent function never produces a value between -1 and 1. When we construct the inverse, that parent range becomes our new domain. The inverse cosecant can accept real numbers as inputs, but it strictly excludes that inner interval of -1 to 1. Following our previous logic, we select the most efficient principal value branch. For cosecant, we isolate the interval from -pi/2 to pi/2. But there is a fatal anomaly hidden inside the selection. The y-axis itself acts as a vertical asymptote directly in the middle of our chosen interval. To prevent the inverse function from breaking, we introduce a surgical subtraction to the principal branch definition, specifically excising the number 0 from the allowed outputs. Successfully engineering an inverse demands a rigorous audit of the chosen slice to identify and excise undefined mathematical voids. We can now move from theoretical derivation to strict practical application for your exams. This layout consolidates the function limits we've just engineered. You see the strict bounds for both inverse cosine and inverse cosecant side by side. Let's put this into practice. What is the precise value of the inverse cosine of -1/2? Think about the deductive logic. The input is a negative fraction. Under our strict constraints, the resulting angle must fall safely into the second quadrant of our allowed principal value branch. The singular mathematically legal output required by these constraints is 2π/3. This diagram maps our answer back onto the restricted curve. The point sits securely at -1/2, yielding exactly 2π/3, proving it obeys the 0 to π boundary. Without the rigorous domain restrictions we built today, you would be trapped trying to provide infinitely many answers to that simple equation. These functions are deliberate, highly engineered constructs, relying on strict domain restriction to guarantee absolute precision.